Good morning, everyone. Today we're going to discuss a new topic, which is the last part of our subject, FINARTS. The TS there stands for time series. So we're going to make use of these packages, forecast, T series. I'm sorry, kindly also, sorry, I forgot to put this quant mode, quant mode. Okay, kindly include that, please, and load the packages. Okay, time series is a very important. Okay, time series is a very important branch of numerical analysis, in particular, also statistics. So here we deal with sequential. The operative word here is sequential. And by this, we mean that your data points are in sequence and it's measured over time. Okay, and the practical use of time series analysis is in many fields, whether it be finance or economics or even marketing and other sciences. Okay, so in finance, you have so many examples of that. Many papers, many researchers are are oftentimes oftentimes make use of time series analysis. So, for example, you'd like to analyze the behavior of certain stocks or its returns. Then, of course, you make use of time series analysis. In operations, you would like to predict the movement of sales or costs. In economics, you'd like to see the movement of inflation rate, etc. These all require time series analysis. So why is time series analysis very important? Because it helps us forecast and create a picture of what might happen in the past based on past values. Oftentimes, time series uh, show three important parts: trend, seasonality, cyclicality, and the last part being random, a random component. The random component which cannot be predicted or modeled. Trend and seasonality are can be modeled. Cyclicality, the cycle is more difficult to model. Okay, so why do uh, why do finance people or economists study time series? Okay, because they would want to understand the underlying process of a particular variable. And sometimes it's also used to detect anomalies in the data. As I mentioned a while ago, these are the components of your time series. The trend stands for the upward or downward movement of your data. Let's say it's going like this. Then you're saying that there is an upward trend or can be going down like this. So there is a downward trend. Another component is seasonality. Okay, these are regular patterns within specific time periods. We're going to look at a very popular data now, which is okay, something's wrong here. Airline passengers, okay, which displays what we call seasonality. So the seasonality are constant uh, movement, ups and downs. They generate peaks. Peaks are the highest values and troughs the lowest value. And they occur with a regular pattern. On the other hand, cyclicality is more difficult to let's say detect because it takes a look at long-term fluctuations and the period is not fixed, unlike seasonality where you have fixed specific time periods. And then of course the last is the irregular component or the noise component, which are just random variation. Okay, so for today, let's use a particular data set. Okay, please change this. We would like to use the air passengers data set. And I think this comes from the quant mode package. So let's run let me clean everything here. Okay, so let's upload the air passengers data set. Okay, so this is coming from, okay, it's still running. And you should have here the air passengers. As you notice, it's under values, which means this is a vector. Okay, this is a vector. If I click this, okay, it will print the time series. Okay, it will not show here because this is not a data frame. It's rather it's a vector. Okay, let's okay, this is wrong. Let's give it a shorter name because air passengers is a long name. Okay, we'll just call it AP. Okay, so that we don't have to write the whole name. Okay, so here I'm creating the object AP, which is the same as air passengers, and let's plot the object AP. Okay, let's see how it behaves. Okay, Control Enter. All right. For some of you who are my students or who were my students in FinLits, uh, you should be familiar with this. Okay, the monthly airline passengers. Okay, let me pause for a while and please ask for the feedback of everyone if you were able to get the data. Monthly airline passengers from 1949 to 1960. Okay, good. Let's wait for the others, please. How about the others? Were you able to upload the air passengers and created an AP object? I now have your AP, which is just the same as air passengers. I just shortened the name. Okay, a few more seconds for your other classmates. Okay, I hope everybody got it, class. All right. So this is the data, airline passengers. This is actual data, US setting from 1949 to 1960. So let's analyze this and see what are the components here. Okay, first of all, you can see that there's a trend. Obviously, there's a trend. There's an upward movement in the data. So there's a trend in the data. So there's a trend component. Now, is there a seasonality component? You notice that there are some peaks, regular peaks here. The data goes up, the airline passengers go up, and then there's this regular downward movement. Okay, so we can say that there's seasonality as far as this data is concerned. And then lastly, cyclicality. Now this is 12 years. It will be very difficult to see any cyclicality. A cyclicality class requires a longer period of time, and it's quite difficult to detect it. Okay, there are some programs, complex programs that can offer some okay, let's say models on cyclicality. Okay, since we have a very short period of 12 years only, then we will not really be able to see cyclicality here because cyclicality involves a long periods of time. Okay, so and then those data points that do not fall under your trend nor your seasonality will comprise your random or, okay, as we said here, the irregular or random component of your data. Okay, so those are the components here, right? Trend, seasonality, cyclicality, we're not able to identify that. And then you have the irregular component or the noise or the random variation. Okay, now when you talk of time series, certain concepts come into play, especially when we deal with some methods. There is a method in time series, a very powerful method called ARIMA, which we're going to discuss maybe later or maybe next meeting together with Garch. Okay, and ARIMA requires that your data should be stationary. What do you mean by stationary? This is not a stationary data. Why? Because there's a trend and there's the variance of the data seems to be, it may be constant or it may not be constant. So in order to illustrate that, let me draw that. So trend, very easy. If there's an upward, okay, or downward movement of the data, then we say that there's a trend. And if the data has a trend, therefore, we say that the data is not stationary. Stationary requires that the data should have constant mean. Okay, so if data was behaving like this, okay, if it was behaving like that, which means that there is no trend and the mean remains constant. Okay, if you get the average at any point, at any period here, the average will be this one. You get it here, then the average will still be this line here. So that means that the mean is constant. Okay, when the mean is constant, it means that there's no trend. And the other one class is the variance. So in order for a data, time series data, to be stationary, okay, the mean should be constant and the variance should be constant. So how does a constant variance look like? Let me clear the drawings first. Okay, a constant variance. Okay, let me start with the non-constant variance. A non-constant variance will look like this one. This is a non-constant variance. Okay, though the mean could be constant because there's no trend, it's not really going up, but the variation of your data is not constant. What do I mean? If I go to this period, okay, you'll find that these are your highest points, these are your lowest points. But when you go here, you notice now that the variance has become very high. Okay, so this is what we mean by non-constant variance. And if your time series display non-constants in variance, then that means that your data is not stationary. Okay, so there we call it the fanning out. It looks like a fan. Okay, when you open a fan, okay, you'll notice that it from the center, okay, from the pivot of the fan, then it goes out, or it can go like this. It can go like that, going inside. This is fanning in. So non-constant variance, non-constant variance. Okay, and there may be combinations like this. Okay? It may be behaving this way. So the variance is not constant. Okay, sorry, it should be this way. The variance is not constant and also the mean is not constant. There's a trend, okay, not constant. The mean is not constant, and the variance is not constant. So we say that this type of time series is not stationary. Okay, stationarity is a very important concept in time series. Okay, it's possible that the mean is constant, just like this. It's like the one I showed you a while ago. Here, the mean is constant. The time series is not trending upwards or trending downwards. Okay, or it's possible that the variance is constant, but there's a trend. Okay, in this case, mean is not constant, but variance is constant. Okay, so this example shows to us that the mean is not constant and the variance is not constant. So in these three conditions, we say that the time series is not stationary. Okay, not stationary. So when is time series stationary? It is stationary when there's constant mean and constant variance. So if at least one of this is not constant, then you have a non-stationary time series. Okay. Now, instead of just looking at your time series manually, okay, because you can identify if the time series is not stationary by just looking at the plot. However, there are statistical tests that we can use. One of the popular ones, but there's a weakness here in this test, is the augmented Dickey-Fuller test. This one. So this test has the null hypothesis that the time series is not stationary. In other words, another technical way to put this is that it has a unit root. When you say it has a unit root, it means that the time series is not stationary. Okay, so if I run this, so ADF the test, okay? So we're testing whether AP, our airline passengers, is stationary or not. Now we know that it is not stationary, okay, because it has a trend. And as far as the covariance is concerned, it may or may not. It's quite difficult to assess via the plot. But here, you can see that the p-value is 0.01. So what does it tell us if the p-value is 0.01? It lends us to reject the null hypothesis that the time series is not stationary. Okay? Which means that the alternative hypothesis is that the time series is stationary. All right, now there's a conflict here because we said that the time series is not stationary, right? If we plot here, obviously there's a trend and there seems to be non-constant variance. So we can say that the time series is not stationary. However, in this case, the ADF test tells us that we should reject the null hypothesis that the time series is not stationary. Okay, so I purposely included this so that we know there are notes here, class. There is a weakness as far as the ADF test is concerned. Okay, the ADF test shows statistically that statistically negative test statistic here, negative 73186, which suggests the null hypothesis of a unit root is rejected. Okay, which is wrong. Okay, which is wrong. So the ADF test gave us a misleading result in this case. Okay, now there's a reason for that. Okay, sometimes the ADF test will give us a quote-unquote faulty conclusion. Okay, it's not able to really sometimes test if the presence of especially if the data has strong trend. Okay, sometimes it will give us the wrong inference. So enter another test. So we have it's best to use two tests at the same time. Okay, you have the first is the ADF test, second is the KPSS test. Okay, so for the KPSS test, okay, so here the null hypothesis is that the time series is stationary, or it has no unit root. Okay, it has no unit root. So this is the code to test that KPSS underscore test. Okay, I'm creating this object, and then the test is KPSS dot test. We're testing our object, and then the null hypothesis is that there's the presence of a trend. Okay, so that's what we're testing. There is a presence of a trend. So if there's a trend, then the data is not stationary. Okay, if you run this, okay, the p-value is 0.1. Okay, and the null hypothesis is that there is a trend, or the data is trend stationary. Okay, sorry, there is a trend. Okay, the data is trend stationary. All right, so what's the null hypothesis? What's the p-value? 0.1. So the test is that it's trend stationarity. Okay, so with p-value equal to 0.1, then we fail to reject the null hypothesis that there is indeed a trend. Okay, if there's a trend, then the data is not stationary. That's what this is saying. Okay, the inclusion of null is equal to trend here indicates that there is a trend. So p-value is 0.1, therefore we fail to reject the null hypothesis that there is a trend. So if there's a trend, then there is if there's a trend, then the data is not stationary. All right. Now, if you take a look at, anyways, again, this one class, what did I do here? If there's a trend, one of the ways to remedy or to remove the trend is to get the log of the data. All right. Now, remember, when you're dealing with certain models in time series analysis, it's important that the data is stationary. Now, if there's a trend, then the data is not stationary. Okay. So how do we address that? We do what we call transformation. And one of the transformation is to get the log of your data. Okay. So here, if you take a look at this code now, we're still using KPSS.test. However, we're doing some transformation to your AP dataset. We're getting the log. We're getting the log of that. Okay. And if you run that class, may I ask you what is the inference? What does that say about our test? What's the p-value and what's the conclusion? Remember, the null hypothesis is that the the data, okay, our data has trend, aka it's not stationary. So if you run this class, what you're testing is not AP but the log of AP, because getting the log of a variable of a time series, okay, will oftentimes address the trend. So if you want to remove the trend so that the data becomes stationary, then you get the log of your data. Okay, please chat in the chat box. What is the p-value, please? What is the p-value and what's our inference? P-value and inference. So remember, the null hypothesis is that there is a trend or the data is not stationary. So what's our conclusion? If we get the log, if we subject the object AP into its log and then after that get the KPSS test. 0.1. James, you're using log AP, this one. Okay, 0.1 pa rin. Fail to reject pa rin. Okay, sige, thank you. Let me run it. Let me see. Yeah, you're correct, 0.1. So therefore, we fail to reject the null hypothesis that the data is not stationary, right? Okay. Now, why is that, class? Because getting the log of your data set was not enough to remove the non-stationarity. Okay, I'll discuss that now here. Okay, so if you take a look at this one, okay, remember, let me just our AP is this one. This is our AP, and it is not stationary because it has a trend. In fact, we can also say that perhaps the variance is also not consistent, not constant, because it seems to be fanning out, although we only have a few years. Okay, but we can say, class, that the data is really not stationary. And we said that you have to transform this and make the data stationary. Make it lose its trend and make the variance constant. So how do we do that? Then we have to do some transformations. And for the transformations, there are many ways to transform it. Okay, one of the most perfect combination is to get the log first of your data and then get the difference. Okay, so get the log. Okay, dali lang may nasa waiting room daw. Inopen ko na to Right. Where's the waiting room? Asan na yan? Wala. Waiting room, waiting room. Andito naman James. She's here. Sophia, are you here? She's here. Sophia. Hello, Sophia. Kasi andito siya sa but she's not responding. Okay, kasi wala, I don't see anybody inside the waiting room. Okay. All right. So if you take a look at this, class, what we did here was to get the log of your data, and then log of your data, and then get the difference. When you say you get the difference, you subtract your data, the data at, let's say, data today minus the data yesterday. Okay, so that's what you mean by differencing. So you're actually creating a new data set. Okay, so let's take a look at this. First, I'll get the log. I'll create this object called log air, okay, which is the log of AP. So if I look at log air, if I view log air, okay, this is now your data, and it's different from the air passengers. How did we get this data? We got the log of your air passengers. There are two Sophias in this class. Okay, but I don't see anyone in the waiting room kasi.
Or she's just experiencing daw po network connections, but she hasn't left the Zoom po ata, sir.
Okay, but I think I disabled the waiting room so anybody can just step in. Okay,
Noted,
thanks,
sir.
James.
Yeah.
Thank you. All right. So what were we doing? We got the log, and then we got the difference here. Difference. So we now have difference here. So if I print diff log air, okay. So you now have a different time series. Okay. And please notice that there's a reason why we're getting the log first and then getting the difference, because doing it the reverse way. So for example, I get first the difference of AP. Okay, so I'll call this DAP. So I'm getting the difference of AP, and then I'm going to create an object called log DAP, which is the log of your DAP. Okay, so it tells me that there are not a number error produced. So why is this so? Okay, so please take note that I'll just put here, take the log and then difference. But not the reverse. Okay, so you don't get the difference and then get the log. What you do is you have to get the log first and then get the difference. And if we plot now, okay, if we plot now the log difference data, which is diff log air, okay, you can now see that, okay, the data now has no trend. The data also does not have uh, it has constant mean and constant variance. Okay, and it's now different from the AP data, which has a trend. Okay, so in this part of the discussion, we said that one important concept in time series analysis is the concept of stationarity. Okay, and a time series is stationary if it has constant mean, which means it has no trend, and if it has constant variance, which means it's not fanning out or fanning in. The variance remains constant all throughout. Okay, and if it exhibits trend or non-constancy in variance, then we'll have to transform the data. And one of the most popular way is to get the log and then get the difference, but not the reverse. Okay, if you get the difference first and then get the log, then you'll have a problem because there will be NANs, not a numbers produced. Because you cannot take, imagine, okay, if you get the difference first and you have this data, you cannot get the log of a negative number. Okay, for example, I'll copy this, Control C, then log. Okay, so I'm getting the log of a negative number, and what does it tell us? Not a number. Okay. All right. May I pause for a while and please chat, please, class, if you are able to follow along. Any questions? I would appreciate any feedback from your end. Okay, thank you. How about the others? Okay, good. Thank you. Okay, I hope everybody's able to follow along. So we can see that one transformation that we did was actually two transformations. We got the log first and then get the differencing. And the data that we created after we plotted it turned out to be this way, this one. And you can notice that the trend has now been removed. Okay? and the uh, and the variance is now constant. Had we just gotten the log, okay? So for example, I'll create this object LAP, and then I got the log of AP, and then I plot LAP. Okay, let's just see what happens if you just get the log of the data and then plot the data itself. Notice here that, okay, by getting the log of the data, it really did not address the trend of the data. Getting the log might cure the non-constant variance, but it will not cure the trend. Okay, it will not remove the trend. However, if we got, for example, the difference of the data, DAP, which is diff AP. Okay, let's see what will happen to your, and plot the AP. Just by just getting the difference, okay, Control Enter. Okay, now you can see that it remedied the trend. Okay, there's no more upward motion. However, okay, getting the difference of the data will not address any non-constancy invariance. You can see here that this is, obviously there's a fanning out, okay, which means that this is not constant variance. So a proper combination could be, the best way is get the log and then get the difference. Okay, but not the difference and then the log, because that will render NANs. Okay, so here, what is this process? We got the log first and get the difference and then plotted it, and you can see that it was able to address the non-stationarity. Okay, all right, I hope that's clear, class. And if we check both the ADF and the KPSS test, control enter. Okay, I haven't run this. Where am I? Here, I'm sorry, here. ADF and control enter. Okay, what do you have here? For the ADF test, okay, what does the ADF test tell us? The null hypothesis here is that the time series is not stationary, okay? The time series is not stationary. And with a p-value equal to 0.01, then it's telling us that we reject the null hypothesis that it is not stationary. The time series is indeed stationary. So as far as the ADF test is concerned, we're okay. And also the KPSS test, which has a null hypothesis that's opposite that of the ADF test. Here, the null hypothesis is that there's a trend, okay? It's trend stationary, there's trend stationarity, okay? Right, so the p-value is 0.01, 0.1, therefore, what's our conclusion? Okay, wait, diff log air, am I correct? Diff log air. So there is a trend, okay? And 0.1 is, okay, wait, why is this like this? KPSS test, 0.1. Okay, our null hypothesis is that diff log air has a trend. Okay, why is the p-value? Like, sorry, class, I got confused here. Okay, so for the KPSS test, null is equal to trend. So that means that, okay, there is a trend. Okay, that's correct. There is a trend. So we fail to reject this. But when we use diff log, am I missing out something here, class? Where's my diff log? What were you getting, class? A diff log. Diff log for your using KPSS test. Am I getting the wrong answer here? Class? May I know what you're getting, class, for the KPSS test? For this one. This one. KPSS test, point 1. What are you getting, class? Same. Okay, but why is our conclusion wrong here? Point 1, which means that we fail to reject the null hypothesis that there is a trend. But diff log air does not have any trend anymore. Plot diff log air. Plot diff we plotted this. There. So no stationary. This is stationary already. So if we're hypothesizing that the trend, it has trend stationarity, which means that, oh, wait. uh, let me clarify class the meaning of, let me clarify the meaning of trend stationarity here. Okay, here, it's AP. Okay, let me check first. I'm sorry, because we're having conflicting results here. Here, when we tested using KPSS test AP, which has trend definitely, then we're getting a p-value equal to 0.1. Here, on the other hand, we're testing already diff log air, right? Same test, KPSS test. And the p-value is still 0.1. Okay, so there's something wrong with the KPSS test here because and it disagrees with the ADF test. The ADF test tells us that the time series is stationary already. Okay, so let me leave this class. Let me check this first because I don't know if they changed some of the parameters for KPSS test, but definitely this is wrong, class. Sorry, the first test of KPSS test is just for AP, okay? And for AP, okay, 0.1, which is correct because the null hypothesis is that our data exhibits trend stationarity, okay? Or our data, okay, there is trend stationarity, so we fail to reject that, okay? No trend stationarity. Okay, here, same thing. Diff log air, again, no trend stationarity. So it cannot be the same answer. 0.1, and here it's 0.1. Okay. For AP, it's 0.1. For diff log AP, it's also 0.1. So there's something definitely wrong about this because it's lending us to the same conclusion. Okay, so let me check this class and I'll get back to you on Thursday about this. Okay, in the meantime, let's now continue our our discussion. Okay, so here we're looking at decomposing your time series. You can decompose your time series into seasonality, into trend. Okay, using the STL function. Okay, so let's use here let's choose the AP data here. Okay, so let's decompose the air passengers. STL AP. Okay, S that window is equal to periodic, and then let's run this, and this gives us the here. This is now the decomposition. This is our original data. This is the seasonal component. This is the trend component. This is the irregular random component. Okay, so we were able to decompose our data into its seasonality component, trend component, and the irregular or random component. Okay, so what are the different methods in modeling time series, in predicting or forecasting time series? There are several methods. So we're going through all the most of the methods. You have simple moving smoothing methods like simple moving average or exponential moving average. Okay, then we're going to take a look at exponential, okay, exponential smoothing, and then we'll go to regression, and then we'll go to ARIMA, okay, and the last we'll go to steady space, okay. So we're going to learn 6 methods by which we model time series, okay. So let's start first with the simple moving average. Okay, so I have here some notes which I hopefully you'd be reading. Okay, I will not anymore. What's important here is the lag size. Okay, so the window size refers to the number of periods used in the averaging. Okay, all right. So this is the equation, class. Okay, so this is the equation for a simple moving average. Simple moving average at time t is equal to 1 over k. K is the lag. So of the summation, okay, from I is equal to t minus k plus 1 up to t of y sub I. Okay, all right. So what does this mean? SMA is the value of the moving average at time t. K is the window size or the lag, and y sub I are the data points over the period of the window. Okay, so let's uh, let's have an example for this. Okay, here, class. Let's have this example of a simple moving average, and we'll be using the lag 12. When you say lag 12, what you're going to do is you get the previous 12 values and then get the average. So that will now be the value of your first first value for your model, for your simple moving average. So here we're creating this object SMA 12, and we're using the function SMA, simple moving average, for our data AP, and then our lag is equal to 12. Okay, our lag is equal to 12. And then let's plot this, class. Plot AP and also include the lines SMA 12. Okay, so let's run this. And you can see here, okay, this is our air passengers. The red line here is your SMA 12. And you notice SMA 12 starts at it starts at line 12, okay, at year 12. So what's the value equal to? It's equal to the average of the first 12 observations. Okay, so notice it does not start on 1949. It starts 12 periods after here. Okay, and what do you notice about the SMA? The SMA, simple moving average, notice that it smoothens out the seasonality. So it's just like a curved line, okay? And it's not able to model the seasonality. Okay, parang average lang siya, no? Okay. So any question about this? Kindly please chat in the chat box if this is clear so far. SMA, simple moving average. Okay, and of course, let's experiment. Let's make the simple moving average 24. Okay, and it becomes your 24-month SMA. If you plot this, okay, you'll notice now that it starts on 24th month. There. And you notice it's smoother now. Okay, it's smoother. So if you're going to compare SMA 12 and SMA 24, aside from the fact that SMA 12 starts on the 12th year, while SMA 24 starts on the 24th year, you notice that if you have a bigger lag here, 24, as compared to a lower lag, okay, let's C. Okay, let me just go here. Oh, sorry. Control C. I'm going to make this 24. And I'll make this 12. Okay, so this is 24. Okay, I have these two plots. One is your SMA 24. And one is your, wait. Here, this should be 24. SMA 24, sorry. All right, you can see that the SMA 24 starts on the 24th month. SMA 12 starts on the 12th month. And you can see that the SMA 24 is more smooth. Okay, if I add another one, Control C, and then I make this Control V, SMA 36. Okay, SMA 36. N is equal to 36. And this is your 36. All right, enter. Take a look at there, SMA 36 class. So almost just a straight line. Okay, so that's the difference between the lag that's smaller. The lag that's smaller is more, let's say, it's less straight as compared to the higher lag. Okay. All right, so that's an example of a simple moving average. It's really simple. You just get the lag that you're interested in and just get the average of the past n lags. So if on the other hand, okay, I'll add another one, sorry. Just to Control C, just to differentiate class, Control B. If I use, let's say, SMA, let's say 4, n is equal to 4, and then this one is, this is 4 months, and then n SMA 4. Okay, again, if I plot all of them, you can see the difference, class, for SMA 4. Okay, you see, class, it's able to mimic more your actual data. So the lower the lag, okay, the more it's able to mimic your data as compared to the higher lag. All right, so I think I placed here SMA 12, 24, and 36. If you do use 36, class, here, it's here. Lag values, so I have here 12, 24, and 36. So I have here a function for lag in, what are the lag values? 12, 24, 36. So what it will do is that it will replace each of these by 12, 24, and 36. Okay, so let's run this. Okay, there. All right, so this is the combination class. This is 12, 24, and 36. So if I put here 4, 4, 12, let's see what happens. Okay, you can see now, evidently you can see the 4, class. Okay, you can see the 4 as compared to 12, 24, and 36. The 4, the lag 4, is more pronounced. It's able to follow more the movement of your time series, okay, as compared to the ones with larger lags. Larger lags class means it would more likely be a smooth straight line or quite a straight line. All right. So, okay, let me see what I did here. So what I did here was, let's compare, when we model class, we can compare the results by using some metrics. One metric is the Ramsey. Ramsey means root mean square error. So what does this do, class? For Ramsey, okay, for example, let me use this one. Okay, here. Ramsey class is, what you do is root mean square error. You get the actual data here and the predicted value is your model. Sorry, a straight line here. Okay. So this is your actual data, right? This is your predicted data. So the difference between this is your residual error. Error, okay? So there are several errors here. Your red line is your predicted. Your actual line is your, well, actual value. So the difference between your predicted, the value on the line, on the predicted value, and on the actual, the difference between them is error. So Ramsey root mean square error means, okay, we're not going to get the mean of the errors because the mean will be 0. So you're going to get the square. So error squared. So get all the errors and square it, and then get the average, and then get the square root. So that's your Ramsey. Root mean square error. Square the errors, get the average, and then get the square root. And of course, the lower the root mean square error, the better. Okay? So we know that if we compare the Ramsey of your 12 or your 24 or your 36, okay? So let's do this. So let's compare here. Let's replace this by 4. Okay, 4, 24, and 36. Okay, let's see. So this will now, what will this do is, this is a function for Ramsey, and the inputs are actual and predicted. Okay, so now take note that you have several, the data for log of 4 will be more than the data for 24, or it will be more for the more than the data for 36. Since for log 36 you're already starting at period 36, then you have fewer data, then you have fewer residuals. So that's why what we're going to do here is we're going to remove the NAs in the predicted values. Okay, because if you get the log 4 and then compare it with the log 8, log 12, log 4 will have 8 more, or log 24, I mean, log 8 will have 16 more values. So we cannot compare those that do not have values, right? So what will be done here is that do not include the NAs here. That's what that means. Okay? And once we remove the NAs, we get the square root of the mean of the difference. Okay? And then squared. So this is your Ramsey class, this one. Actual of the valid index minus predicted of the valid index. Take note, the valid index are those without the NAs. And then square it, and then get the mean, and then get the square root. And that's used for log values of 4, 24, 36. And without solving this class, we know that 4 will outperform. It will have a lower Ramsey compared to 24 and 36. Okay, so let's print the Ramsey results. Let's run this. Okay, and now you can see that here. All right, The Ramsey for 4 is 56. The Ramsey for 24 is 131. And the Ramsey for 36 is 137. So you have more Ramsey for the log 36, and that's expected class. So it tells here that the longer object is not a multiple. What we can do is, I gave you another code here. This will really trim. Here we did not trim the excess values. Here it will trim it. It will remove the NAs here class, NA.omit, okay? Here it did not NA.omit. So just run this class, okay, so that we don't get that error, okay? Tagal. Okay, there you go. Oh, sorry. To make it more comparable, I'll make this 4. 4, 24, and 36. Okay, there you go. Ramsey for log 4 is 36. Ramsey for log 24 is 57. And Ramsey for log 36 is 69. All right. Okay, I think I have time for this one. Now, SMA, a simple moving average, is used in stock trading. So this is an example. This is an application of SMA in stock trading. Okay, it's used, as you know, SMA will smooth out the price data. Okay, the purpose of the SMA is to point to the direction of the trend. Okay, so one popular method in stock trading is taking a look at the moving average crossover. So you're comparing the short-term moving average, okay, and the long-term moving average. So let's use this one class. So there's a package, if you're not yet familiar with quant mode, this is a package where you can download stock prices. Okay, so please, we ran this a while ago already, so I ask you to load this. So we're going to use the get symbols for those of you who are not familiar with this. We're going to use the get symbols function, and we're going to download Apple. So the source is coming from Yahoo Finance, and let's identify the date from January 1, 2020 up to system date, which is today. Okay, and here I'm creating 50 day simple moving average and a 20-day, 200-day simple moving average. And the function is SMA. We're just going to use the closing prices of Apple and identify n is equal to 50 and n is equal to 200. Okay, so let's run this first. Okay, I hope you have already run quant mode. Control Enter, and then it will create now SMA. So we have Apple first, and then, okay, where is my environment? So it will now run, okay, SMA 200 and SMA 500. If you take a look at SMA 50, right? So take note that the first 49 observations are NAs, because what happened is that you get the first 50 and then get the average, and then that will now be our value, this one. Okay. So for the SMA 200, it will be you average the first 200. So there will be more NAs here. Here, NA, first 200. Okay. And then this comes in here, which is the average of the first 200. So that's what happens when you have simple moving average. All right, now let's plot this. Okay, plot the closing of Apple. Okay, include the lines of SMA 50, lines for SMA 200, and put some legends in our plot. Okay, so let's plot this. Control Enter. Okay, now you can see a plot of your Apple. Okay, The red line here is your SMA 50. Okay, and even without looking at it, you'll know that that's SMA 50 because it started earlier. This is your SMA 200. So what's the rule among traders, stock traders? Okay, for example, if the 50-day moving average SMA 50 crosses above the 200-day moving average, it is often interpreted as a buy signal. It means that stock prices will continue going up, so it's a good time to buy. While a crossover, okay, where the SMA 50 goes down below the SMA 200, then it's a sell signal, which means that prices will tend to really go down. So it's better to sell now. Sell now your asset. Okay. If you take a look at this class, here is a crossover. Here. Crossover here, right? So this one is a sell signal. Why? Your 50-day SMA crosses below your 200-day SMA. On the other hand, this one is a buy signal. Buy signal. Why? Your 50-day simple moving average crosses above the 200-day moving average. Okay? So I hope this is clear, class. This is a good example of a practical application of SMA. So SMAs have their uses. It's not only used for plotting. Okay. So let me just introduce the next one, which is exponential moving average. You have your details here. The formula is EMA. It's different from SMA, but these are both moving averages. Here you have the presence of alpha, and then 1 minus alpha times EMA T minus 1. Okay, so I hope you read through this class. And let me just give you this example, and then we close for today. So we use the EMA function. Okay, EMA is quite different class from, but they're okay. Where's my comparison? I have a comparison here between EMA and SMA class. So okay, here you're computing EMA 6, EMA 12, and EMA 24. The function is EMA underscore function. Okay, so here we're plotting so that you can see what's the difference between EMA 6, EMA 12, and EMA 24. Okay, what happened? Did I? Okay. Did I run the packages? Sorry. I didn't run the packages, I'm sorry. There. Because EMA comes from the TTR, technical trading in R. Okay, just this last one class. Where's my EMA? Here. Okay. Anyway, let me check this class. Huh? Yeah, were you able to run it, class? We'll continue with this next meeting. It's already time. So next meeting, class, we're going to finish this one and then move on to introduction to GARCH. Okay, introduction to generalized autoregressive. Okay, very sorry for this. Let me check my function. Maybe I made a mistake here with my function here. Okay, wait. Wait. Okay, I'm sorry. There was a mistake, class. This one should go below. Okay. This one, run this first class here. Run this one. Okay. The EMA function class is this one. Okay. I'm sorry, I interchanged. So this is the EMA function. That's why it's not running, because you don't have the EMA function. And when I run this now, okay, kindly please remove this one, Control X, and move it here below. Okay, my apologies. Control V. All right, so here you can see, class, the difference between, this is EMA 12 here. EMA 12 exponential moving average. Here is the difference between EMA 6, 12, and 24. Okay, now take a look at this. What's the difference between them? The longer the lag, class, just like SMA, no? The longer the lag, the more smooth it is. Take a look at this violet. This is EMA 24 months. EMA 6 months is the red one. So it's able to follow more the original data, just like the SMA. Okay, so good. Thank you so much, class. Let me stop recording now. Okay, I hope